Dear students, welcome to my YouTube channel आओ chemistry सीखें. Let's enjoy chemistry. In this fourth lecture of electrochemistry, we are going to study one method of determination of transport number. So today's topic is determination of transport number by moving boundary method. This method is useful for BSc students. So आओ chemistry सीखें. Let's enjoy chemistry. Dear students, let's have a recap. Last time we studied that whenever current or electricity is passed through an electrolytic solution, then ions start moving towards respective electrodes. Cations move towards cathode and anions move towards anode. And charge in the solution is carried by these ions. Each type of ion carries a fixed amount of charge or electricity. If total electricity or current flown through the solution has certain value, then a fixed part of this total current or electricity is carried by a particular type of ion. This fraction of total current carried by a particular type of ion is known as its transport number, and it is generally written as Ti. So by formula, Ti or transport number is the charge or current or electricity carried by a particular type of ion divided by total current, total charge or total electricity flown through the solution, or mathematically Ti is equal to small qi upon capital Q, where small qi is the electricity carried by ith type of ion and capital Q is the total electricity flown through the solution. Transport number is also known as transference number. As we discussed, it is designated by the symbol Ti, and since it is a fraction of current or electricity carried by ith type of ion, we can have an idea that sum of the transport number of all type of ions present in the solution will be equal to unity. Let us say transport number of cation is T plus and transport number of anion is T minus. Then sum of these two transport numbers will invariably be 1. Transport number of ions can be determined experimentally, and there are generally three methods which are employed for the experimental determination of transport number. The first one is known as the moving boundary method. In this method, the rate of motion of boundary between two solutions under the influence of current is studied. The second method is based on the procedure originally proposed by a scientist by name Hitov in 1853. So the second method is known as Hitov's method. It involves the measurement of changes of concentration in the vicinity of electrodes. And there is one more method which is based on electromotive force measurements of suitable cells. Third method is known as EMF measurement method. Today in this lecture we are going to discuss the first one, moving boundary method, in detail. Moving boundary method used for determination of transport number is based on direct observation of migration of ions. This method is based on the idea employed by Laws and Wetham for the study of speeds of ions. In order to determine transport number of given type of ion by moving boundary method, we have to fill two type of electrolytes in an electrode. The first one is principal electrolyte and the second one is indicator electrolyte. Principal electrolyte is the electrolyte having the ion for which transport number is to be determined. An indicator electrolyte has certain properties. First, it should have common ion with the principal electrolyte. Second, indicator electrolyte should have slower ion. And the third one is indicator electrolyte should have higher concentration so that it has to be heavier than the principal electrolyte. Let us understand moving boundary method in detail. We take a vertical tube of uniform bore. It has thistle ends. Now indicator electrolyte and principal electrolytes are filled in this thistle tube. Indicator electrolyte, as we said earlier, has to be heavy or has to have higher concentration. So it comes at the lower end, and principal electrolyte, which is the lighter one or having lower concentration, fills upper part of the tube. And there comes a boundary between these two type of electrolytes. Now electrodes are dipped in principal electrolyte and indicator electrolyte, which is in turn connected with source of external EMF. Dear students, let us try to understand the principle and concept of moving boundary method by determining the transport number of hydrogen ion using this method. For this, we need a setup like this, where thistle tube will be taken as the conductivity cell, and as we have studied, we need two electrolytes to be filled. One will be the principal electrolyte and the indicator electrolyte. The principal electrolyte is the electrolyte that has the ion for which transport number is to be determined. In this case, our aim is to determine the transport number of hydrogen ion. So we have taken HCl solution as the principal electrolyte, which is filled here in the thistle tube. It has been shown with yellow color. And we need an indicator electrolyte. An indicator electrolyte, as we have studied, should have common ion with the principal electrolyte, and second, its counter ion should be the slower ion, and third, indicator electrolyte should have higher concentration. So we have taken HCl as the principal electrolyte. Now what can be the possible indicator electrolyte? One thing is for sure, the Cl should be the common ion with the principal electrolyte. That means indicator electrolyte must have chloride ion. Then second, indicator ion's cation should be slower than hydrogen ion. And third, concentration of indicator electrolyte should be more. So in this case, we have taken cadmium chloride as the indicator electrolyte. It has common chloride ion. Then second, its cation CD2 positive is slower than hydrogen ion, and we take concentration of CdCl2 in such a way that it becomes heavier than HCl solution. So when it is filled in the thistle tube, it occupies the bottom part or lower end of the thistle tube. Now when we fill these two electrolytes in this thistle tube or conductivity cell, CdCl2 and HCl solutions have different densities or different concentrations. As a result, a sharp boundary forms between these two. We term it as the initial boundary. And then we dip or immerse two platinum electrodes in the solutions, one in HCl, other in CdCl2. And then we connect these two electrodes with the source of external EMF or battery, and other electrode is connected with a coulometer. The function of coulometer is to measure total amount of electricity flown through the solutions. Coulometer measures this electricity with the help of second law of electrolysis given by Faraday. Now coming to mathematical part of the moving boundary method. Here is the picture. HCl solution is filled as principal electrolyte. Cadmium chloride solution is filled as indicator electrolyte, and concentration of cadmium chloride, which is shown here with a blue color, is higher than that of HCl solution. As a result, cadmium chloride occupies lower part of the conductivity cell and HCl comes at the top of cadmium chloride solution, and there forms sharp boundary between these two solutions. Let us say concentration of HCl solution filled here is equal to C gram equivalents per liter. Gram equivalents per liter indicates concentration is measured in terms of normality. So normality of HCl solution is C. Let us say cross-sectional area of this tube is a centimeter square. Now what happens? Now what we do? We complete the circuit by closing this key. As the circuit completes, electricity starts flowing through the conductivity cell and platinum electrode connected with the negative terminal acts as cathode and this platinum terminal acts as anode. So what happens? Hydrogen ions, which are positively charged ions or cations, start moving towards their electrode under the influence of external electrical field. As the hydrogen ion moves, so does the cadmium ions. They also start moving towards cathode. But ionic mobility of hydrogen ion is higher than that of cadmium ion. As a result, when circuit complete, initial boundary starts moving, but cadmium ions cannot overtake hydrogen ion, so the boundary remains between these two solutions. Here is the picture when the key is closed and circuit completes. You can see here the boundary starts moving upward. It is due to movement of hydrogen ions and cadmium ions towards their electrode, which is cathode. Let us say after a certain time the boundary moves by a distance of L centimeter. So what happens? Movement of boundary to a distance of L centimeter means HCl solution has moved upward to this distance. So when boundary moves a distance is equal to L centimeter, we can have some idea that what will be the volume of HCl solution which has moved upward. It is not that much difficult because cross-sectional area of this tube is A and length of the boundary moved is L. Then volume of HCl solution moved upward will be equal to length into cross-sectional area or L into A centimeter cube. This is the volume of HCl solution. Our next aim is to find out how many hydrogen ions have moved upward when L into A centimeter cube of HCl moved upward. So it is again simple because concentration of solution is C gram equivalent per liter. That means 1 liter of solution contains C gram equivalents of hydrogen ion. 1 liter, if we convert into centimeter cube, it becomes 1000 centimeter cube of solution contains C gram equivalents of hydrogen ion because 1 gram equivalent of HCl will contain 1 gram equivalent of hydrogen ion and 1 gram equivalent of chloride ion. So 1000 centimeter cube contains C gram equivalents of hydrogen ion. That means L into A centimeter cube of solution will contain C upon 1000 into L into A gram equivalent of hydrogen ion. I think this much is clear so far. That means when a boundary moves to a distance of L, these many gram equivalent of hydrogen ions have moved upward. So number of gram equivalent of hydrogen ions moved upward is equal to L into A into C upon. Now, second law of electrolysis states that 1 gram equivalent of any substance carries 1 Faraday electricity. Since these many gram equivalents of hydrogen ions have moved upward, the question comes, what will be the amount of electricity carried by these many gram equivalents of hydrogen ion? For that, we use this conversion factor. 1 gram equivalent is equivalent to 1 Faraday of electricity. So L into A into C upon 1000 gram equivalent will be equal to 1 into L into A into C upon 1000 Faraday of electricity. So this is the charge or electricity carried by these many gram equivalents of hydrogen ions. As we discussed, Faraday's second law of electrolysis states that 1 gram equivalent of ions carry 1 Faraday of electricity. So these many gram equivalents will carry equal Faradays of electricity. That means electricity carried by hydrogen ion is equal to L into A into C upon 1000 Faradays. Now, let us suppose when circuit was complete, the total amount of electricity passed through the solution was equal to Q. How will we measure this electricity? The answer is simple. Coulometer gives idea about total amount of electricity passed through the solution. So, total amount of electricity passed through the solution measured in the coulometer was equal to Q. Now, the final part of the concept comes. By definition, transport number means it is a fraction of electricity carried by particular type of ions. Here, our aim is to determine transport number of hydrogen ions. So, when total amount of electricity was Q Faraday, out of these Q Faradays, these many Faradays of electricity was carried by hydrogen ion. So what is the transport number of hydrogen ion? It is equal to electricity carried by hydrogen ion divided by total quantity of electricity passed through the solution. So transport number of hydrogen ion is equal to LAC upon 1000 upon total quantity of electricity, that is Q, or transport number of hydrogen ion is equal to LAC upon 1000 Q. So this was the mathematical concept of moving boundary method. Dear students, finally we will polish our concept of moving boundary method by solving a numerical. This numerical has been taken from the book Physical Chemistry by Puri Sharma and Patania. Here is the question. Calculate the transport number of hydrogen ions and chloride ions from the following data obtained by the moving boundary method using cadmium chloride as the indicator electrolyte. And here is the data. Concentration of HCl solution is 0.100 N, that is normality. Mass of silver deposited in coulometer is 0.1209 grams. Moment of boundary is equal to 7.50 centimeter. Cross section of the tube is 1.24 centimeter square. So now our purpose is to solve this numerical to get better understanding of moving boundary method. As we have solved out, transport number of hydrogen ions is equal to L into A into C upon 1000 Q, where L is the distance moved by boundary. It is given as 7.50 centimeter, and A is the cross-sectional area of tube. It is given as 1.24 centimeter square, and C is the concentration of solution of HCl or principal electrolyte in normality, and here 0.100 N is the concentration. The final thing comes total amount of electricity or Q. Nowhere in the question the total amount of electricity or Q has been given. So our first task is to find out value of Q. If you remember the lecture, Q or total amount of electricity passed through the solution is measured or determined with the help of coulometer. Coulometer is an instrument that works on second law of electrolysis. It says that 1 gram equivalent of any ion carries 1 Faraday of charge. So in this case, as you can see, mass of silver deposited in the coulometer. That means coulometer contains some silver salt. When electricity passes through the coulometer, silver ions get reduced and deposit in the form of silver. So this is the reaction that takes place in the coulometer. Look carefully at this equation. Here, if we measure it in terms of moles, so 1 moles of electron means 1 Faraday of electricity, and 1 moles of silver means 108 grams of silver. That means when 1 Faraday of electricity passes through a silver salt solution kept in coulometer, it will deposit 108 grams of silver. So 108 grams of silver means 1 Faraday of electricity. But in the present case, only 0.1209 grams of silver have been deposited. That gives 1 upon 108 into 0.1209 Faraday of electricity was passed through the electrolytic solution or through the conductivity cell used in the moving boundary method. So this is the total amount of electricity Q. Now we have got all of our quantities needed to calculate transport number of hydrogen ions. Next thing is to substitute values of L, A and C and Q and find out transport number of hydrogen ions. This is the first part of this question. The second part is to determine transport number of chloride ions. It's again simple because we know that for a given electrolytic solution, transport number of cations and transport number of anions in total is equal to 1 because these are the fractions of total electricity carried by cations and anions respectively. So if we know T plus, that is transport number of cation, we can easily calculate transport number of anions by subtracting that transport number of cation from 1. So in the present case, transport number of chloride ion will be equal to 1 minus transport number of hydrogen ions. Here is the solution. You can find out mass of silver deposited this much. It will help us to find out total quantity of electricity that flows in the circuit, and as I told, it is the result of second law of electrolysis. So transport number of hydrogen ion is obtained by substituting values of L, A, C and Q in this formula. It comes out to be 0.8308. Since it is the ratio of charges or electricities, it has no unit. Final thing, transport number of chloride ion obtained by subtracting transport number of hydrogen ions from 1, which comes as 0.1692. If we sum up these two, it will come as 1. So hope you got the idea about determination of transport number by moving boundary method. Thank you very much.